So the last thing that I discussed on the last video was that most of the drugs that we're going to talk about in pharmacology alter neurotransmitters. They do not, or receptors. There are drugs that alter the action potential on the axon, but they're not selective, so they're not used a lot. So the important thing to understand is what goes on at the synaptic cleft. So this is then my neuron. This is my axon terminal. And in the cell, we have these little circles called vesicles. So they're floating around and they're full of all different kinds of stuff. But the important ones here are full of neurotransmitter. So my pink little dots, I don't know if you can see those, that is neurotransmitter hanging out in the cell. Now, if it's here and it's in these vesicles, is it doing anything? No, it's just there. It's stored. It's like the fat on my butt. It's there. It has potential to be useful, but am I doing anything with it right now? No. So that's important. Neurotransmitter is hanging out in the little vesicles. We talked about the axon, the action potential that travels down the axon. It's an electrical stimulus. And when that electrical stimulus, those ions, because all of our electricity in the body is ions, right? Potassium, calcium, and sodium. Those are the big three. Just like this is us. So, when that action potential reaches this axon terminal, my vesicle moves down to the cell wall, the bottom of the cell. Because remember, this axon, this neuron, it's a cell. It's still a cell. It's a cell like any other body cell. It has a nucleus, it has vesicles, it has all that stuff, or most of that stuff. So it's got these things, and it's got a cell wall just like any other cell. It's just a cell that's part of the nervous system. So when this action potential reaches this axon, these vesicles move down to the cell wall. And they do exocytosis. And they pop my neurotransmitter out here into the postsynaptic cleft. The postsynaptic cleft is just this area between the axon terminal and the body cell. So this is my body cell. What kind of body cell is it, you may ask? Whatever kind of body cell you want it to be. It doesn't matter. This process, this basic process, occurs all over the body. This could be a somatic muscle cell. That's the neuromuscular junction. So if this were the neuromuscular junction and this were a somatic voluntary muscle cell, then what would this be? Acetylcholine. Remember? It would be stimulatory here. It would cause something to happen. So, this could alter ion permeability causing causing voltage-gated channels to open. Or it could also be something that causes a receptor to binds with a receptor and causes the receptor to come to the surface. It could activate a second messenger. It can do a lot of different things, but the important thing to realize is that we have the synaptic cleft, the body cell, and the neurotransmitter here in the cell. Now, let's say we have this receptor here. And I drew it big right here to kind of get an idea. This is a body cell, or this is a receptor on a body cell. So that's my cell wall, and that's my receptor. Now, it's got this neurotransmitter floating out here, and it's a very specific shape. You see how that would fit perfectly into there. It's just like the key on my house. My key works perfectly for the door to my house, and it does not work for the door to your house, or it shouldn't. So, in some places in the body, we have very selective receptors on cells for particular neurotransmitters. Now, with our concept of the ideal drug, we realize that if we can make something that looks just like this, so it can fit into our little key, it's like duplicating my key, we can block that receptor. So depending on the action at that receptor, we could either cause something to happen or we could inhibit something from happening. And that's where we talk about the antagonist and the agonist. So just because something comes in and it performs, when we say antagonist or agonist, antagonist means blocking or stopping, and agonist means doing. But acetylcholine, when it's activated at a receptor on cardiac tissue, it causes heart contractions to slow. So it's activating the receptor for acetylcholine, but it's causing heart contractions to slow down. So just because the receptor is activated doesn't mean that the physiological processes are going up. They could be going down. So the important thing to remember is that an agonist is activating a receptor. An antagonist is inhibiting the receptor from being activated. Okay, so these are my little receptors in the cell wall. And my neurotransmitter is emitted from the vesicle. It has the right key, and it's going down into here. And the next thing that I'll be talking about is the different keys, because every receptor on the body cell is not the same. There are different ones. There's the nicotinic and the muscarinic and all of those, and they're all different. But the important thing, and an important application of this in pharmacology, because I know that this is abstract, but one thing that we've already talked about a lot, and that we're going to continue to talk about because it's such a big epidemic in our country right now, is opioids. And opioids bind to certain receptors in the body called, I believe they're mu receptors. So if we have our cell, we have our little opioid receptor. The opioid medicine, like morphine for example, comes in and binds to this receptor on the cell. And it makes us feel really good when we have opioid bound to our opioid receptors. But what happens when we have too much? We have opioid overdose. And that causes respiratory failure. So you see somebody that is on morphine and their respiration is down to 8 breaths a minute. That is a key signifier that they have had opioid or they're experiencing opioid overdose. So what do we administer in that situation? Narcan. Right? Remember Narcan? How does Narcan work? Narcan, if this is my little opioid guy, Narcan looks just like him. He fits the receptor too. And he maybe even has some stronger affinity for that receptor. So Narcan can go in and he can block it. He can fill that up right there. And when Narcan is in there filling that up, that opioid medicine, it can no longer get in. It can no longer cause that depressed respiration and everything else that comes along with opioid drugs. And that can save your patient's life. So receptors can save a life.